In section 1-3, we're going to look at three objectives. The first one is finding the domain and range of a relation. This is probably not new to you. You probably did it in algebra, but what might be new is considering the context if we have a word problem when we're finding the domain and range. Next, we're going to look at determining whether a relation is a function, and if so, find out if that function is one-to-one. Again, you probably remember this from algebra. Maybe you did something called the vertical line test. Now, what's probably new for everyone is constructing a completely defined model. This model will have 4 parts. I doubt you've seen this before, but this is very important, and you will use this a great deal if you go on to take business calculus, Math 210, or statistics, Math 112. All right, so the domain is the set of all input values. So if you think about algebra, you probably used x as your input variable. Whereas the range is the set of all output values. And again, in algebra, you probably used y for your output variable. Now, we talked about that function notation. So if you have, let's say, f of t here, the domain would be all possible inputs or all possible t's. Okay, and then the range would be all possible outputs, all possible f's. So it might not always be x and y. Think input, domain, output, range. Okay, so there's 2 cases we're going to consider. The first is when our domain and range comes from the context here. Okay, meaning we have a word problem and we have to consider the real world implications here. The second would be restrictions on the functions. So maybe if you remember in algebra, you're not allowed to divide by 0, for example. So let's start with that first case, the context. Okay, the height of an object in meters which is dropped from the Empire State Building Observatory is given by h of t equals 320 minus 4.9 t squared, where t is the number of seconds after the object is dropped. Alright, so let's figure out what our input and output is here. Alright, my input, t is the number of seconds. So here my input is time. Alright, now the output is the height of the object. Alright, so if you look down here, here's my t-axis, and then this is my h of t-axis up here. Alright, so let's start with the domain. We're considering the context. We drop an object and we record its height. Well, I hope you have some intuition that it wouldn't make sense to talk about a negative time, to talk about time before we've dropped the object. Now here in our notes we say t must be positive, but we could include 0, so I probably should have t must be non-negative there. So therefore we know that t must be greater than or equal to 0. We don't want to talk about the time before we drop the object. Alright, so time 0 is when I let go. Alright, so at time 0 I'm right up here. Okay, then I let go of the object. Now we see that the object at some point is going to strike the ground, and it looks like it's around 8. Right here it strikes the ground. But you see how it would not go below the ground? My model doesn't make sense once my object hits the ground. So we don't want to include this stuff over here that's below the x-axis. And similarly, I don't want to include this stuff, this negative time stuff over here. So the part of my function that makes sense in the context is times 0 to something around 8, where we hit the ground. Alright, so now if we want to find out what that time, it looks like it's going to be around 8, is, we have to consider what our height is when we hit the ground. Well, the height would be 0. Okay, so I need to find out, is this going to be a solve or an evaluate? So my height of 0 is an output. So I want to know when 0 equals 320 minus 4.9 t squared. Alright, so this is going to be a solve problem, not an evaluate. I'm not plugging in 0, I want to know when this equals 0. Okay, so the first thing I might do is move this negative 4.9 term to the other side. Alright, now I'm trying to solve for t, so I might divide both sides by 4.9. And that would cancel that out. So then we would have t squared equals, alright, so I want 320 divided by 4.9 gives me 65.306. Alright, and now I want to divide both sides by, nope, we've already done that. What do we want to do next? We want to take the square root of both sides. And that would give me the positive root, which is the root that I want, because we just said the negative time doesn't make sense in this context. So if I do the square root of my answer, I get 8.081. Alright, which we guessed it was around 8 from the picture that we were given here. Alright, so therefore we know that t must be greater than or equal to 0, but we've got to stop here at time 8.081. So the way we would write that is 0 is less than or equal to t, which is less than or equal to 8.081. Alright, so if we look back at our picture, we're going to start at the input variable, the domain. Here goes from 0 to 8.081. Now, if we consider the range here, well, the range is the height. So the height cannot be less than 0, but the maximum height would be up here, it looks like above, a little over 300. So how might we find that? Well, to find the output up here at the beginning at 0, we need to evaluate at 0. So we want to find h of 0, which is an evaluate. So I'm just going to plug in 0 here. So this is going to be 320 minus 4.9 times 0 squared. Well, 0 squared is 0 times 4.9. That term just goes away, right? So we're left with 320. Right? So the maximum height is up here at 320. The minimum height is down here at 0. So we might write that as 0 less than or equal to. Now my output variable is h, height, which is less than or equal to 320. So given the context, time would go from 0 to 8.081, and given the context, the height would go from a minimum of 0 to a maximum of 320 meters. Next, in this example, we have a 400-seat theater, and our revenue from ticket sales is given by 5.75x, where x is the number of people who attend the movies. So my input here is people, or tickets sold. Now the first thing we realize is you can't say a negative number of folks went to the movies. So the first thing we know is that x must be greater than or equal to 0. Okay, so maybe nobody goes to the movies, 1 person, 2 people, 3 people, but we're also given this information here that we have a maximum capacity of 400 folks. Okay, so we cannot sell more than 400 tickets, so we also know that x must be less than or equal to 400. Now, the tricky part about this one is we cannot sell part of a ticket. So what do I mean? Maybe I sell 0 tickets, maybe 1, maybe 2, maybe 3, but you see I could not sell 4.75 tickets. It's got to be a whole number. So if you remember back to section 1.1, we had natural numbers, which are our counting numbers, but because we want to include 0 here, that would be a whole number. All right, the next step up would be integers, which would include negatives, but we don't want the negative whole numbers. We can't sell negative tickets, so x must be a whole number. Okay, so putting these 3 pieces back together, we know x is greater than 0, but less than 400, and it must be a whole number. We cannot sell half of a ticket or part of a ticket. So my domain here is x is greater than 0 but less than 400, where x is a whole number. Alright, so that was our first case considering the context of the problem. Now, if we don't have a context, sometimes there are restrictions on functions. The 2 most common that we will see a great deal is that we can't divide by 0. Or another way to think about this is your denominator cannot be 0. So I might write that. Denominator, I'm going to abbreviate that, not equal to, an equal sign with a slash, 0. All right, our second case is we can't take the square root of a negative number. Take the square root, I'm going to abbreviate that, of a negative number. Okay, so if we have a square root symbol, right, whatever goes in here must be greater than or equal to 0. Alright, now the range of a function without context is a little tougher. What I tend to do is graph the equation and then try to use a graphical representation. Because then I can just look up and down for my range and left and right for my domain. So whereas the domain is all possible input values, so input was left to right. So let's so we're going to look left to right. All right, so let's go back to that last example we just looked at. All right, so here I'm going to go left and right for my domain. So the left, the farthest I can go is 0, and right, the farthest I can go is a little more than 8. Okay, now for the range, those were the output values. So the minimum was down here at 0, and the maximum is up here at 320. So for those, you're going to go up and down. So for the range, are all possible outputs, so we're going to look up and down. Alright, so let's look at a couple examples here. Alright, so our first example with no context here, we have this function right here. Now, given those for our domain, we said the denominator can't be 0. So do you see here, if I were to plug in a 3 here, 3 minus 3 would give me 0, which is not allowed. Okay, but from the graph, do you see at 3 we have what you might have called an asymptote? There is no value at 3. Okay, so one way to do it is to think about the restrictions on the function and say, well, I cannot plug a 3 in there because that would give me 0. Okay, so if I took my denominator cannot be 0. Well, if I solve that a little further, I add 3 to both sides, I get x cannot be 3. Or what might be even easier is let's just look left to right. If I go left to right, I can take on that value, that value, that value, that value, that value. But do you see how I jump over 3 here? And keep going. Alright, so my domain, I'll use a D for that, is everything except for 3. So the way that we write that is x not equal to 3. Okay, now the range is a little more difficult. Like I said, I'd rather use the graphical representation and think up and down. So if I start down here at the bottom, I can take on this value, this value, this value, this one here, and it looks like I get really, really, really close to 2, but then do you see I jump over here? I jump over 2 here. So we can take on any value except for 2. So my range might be f of x, my output variable, not equal to 2. Okay, so it can be anything other than 2. Alright, let's look at this next one. Now this one, when we think about restrictions on the function, this wasn't one of the 2 that I listed. But let's see here. If I have 2 numbers that are squared, they're both going to be positive, and I add them together and they give me 16. Okay, so these 2, neither of them can give me something that when I square it, it's larger than 16. But the easiest way, again, is to look at your graphical representation. If I go left to right, my domain goes from -2 to 6. So my domain here, we'd say -2 is less than or equal to x, which is less than or equal to 6. Now for my range, I want to look up and down. So the smallest value I can take on is down here. That looks like -5 up to right here. What would you call that? Does that look like 3? So we would say my range then would be -5 less than or equal to y less than or equal to 3. Okay. Now, this one here, this one's going to be tough. We're going to use our technology to help us here. Okay, so I have this function. Now when I'm thinking about domain, I could plug absolutely anything I wanted in there for t. There's no restriction on the function. I don't have to worry about something getting too big or dividing by 0 or taking the square root. Or if you look, if I go left to right, I can take on all values here. If I go to the left, I just get bigger and bigger and bigger. If I go to the right, I just get bigger and bigger and bigger. So this is all real numbers. Right? It could be a whole number, integer, natural number, rational number, all real numbers, anything. Now the range, if I look up and down, do you see I don't go below this value right here, which looks like a little less than -150? Okay, now to figure out, and then I can go up, 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 up forever. Now I need to do is figure out what that value is, which is why we're going to need the calculator to help us. We're going to use the technology here. So first thing I want to do is go to my graph menu and enter my equation. And I'm already given a window that works pretty well here, so I'm going to go from my viewing window. I'm just going to follow what we have in our lecture notes here. So I'm going to go from -5 to 8, counting by 1. And then let's go a y-min of -175 to 175, counting by 50. Alright, assuming I entered that correctly, we should get something similar to what we have in our notes. Yes! Alright, so our first strategy might be to trace, and we see, okay, the minimum value here, if I'm going up and down, would be something around negative, let's see here, what do we get? About negative, that's the smallest I've done so far, would be -161.99. Now to find that exactly, there is a built-in function in our graph solve menu. So I'm going to hit Shift, graph solve, and there is a minimum command above F3. Alright, so the minimum value here is -162. Now let me show you this. If I use the right arrow, the calculator finds local minima. So if I use the right arrow, this local minimum is -37. But you see that this one is definitely smaller than the -37. Alright, so that minimum value is -162. Alright, so my range then we know g of t must be greater than or equal to -162. We never go below there. And then it can keep going up and up and up. Alright, lastly, here we have a radical. So again, if I think left to right for my domain, the farthest left I can go is 3. Or, remember how we said we cannot take the square root of a negative number? So I know that this stuff under the radical, just the x minus 3 part, must be greater than or equal to 0. Alright, if I do a little algebra to solve that, I add 3 to both sides, I get x must be greater than or equal to 3. And that is my domain. So I can be 3, and then it keeps going on and on and on and on over here. Now the range is a little tougher. Like I said, I use the graphical representation. My range here, if I think up and down, the smallest value here is that 5? And then it can get larger and larger and larger and larger. So my range here, h of x, is greater than or equal to 5. Alright, so that's how we might find the domain and range if we don't have a context. Now, I want to make one small point here. If we think about square roots, usually when we take the square root, we have 2 values. So let's think about if I wanted to find the square root of 9. Right, well, usually if I go to the calculator and I type square root of 9, it says 3. Okay, so remember, the square root is the number squared that gives me 9. Well, do you believe me that negative 3 squared, well, that's going to be negative 3 times negative 3. Well, that also gives me 9. So we should have 2 square roots, one positive and one negative. All right, the calculator always gives us the positive root. The calculator gives us the principal root, or the positive root. Okay, so the notation we're going to use, if we have just a square root symbol like here, this is standing for the principal square root, only the positive square root. If we want to consider both roots, we're going to add this notation here, this positive negative, because sometimes it can be a little confusing whether we only want the positive one or whether we need both roots. Alright, so now we are moving to our second objective, determining if a function is, if a relation is a function, and then if so, is that function one-to-one? Alright, so a relation is any rule, alright, or mapping or correspondence. It's just anything that links inputs to outputs. Okay, so there is no stipulation here. Now, a function is a subset of a relation, but it's a special relation for which each input has only one output. Okay, so if I'm going to jump down here, a relation is out here, relation. It's just any rule. Okay, now if my rule has only one output for each input, then we're a subset of all relations, which we are going to call a function. Alright, now if we go a little bit further, a function is one-to-one if, well, we have two criteria here. The first is it's got to be a function, right? So each input has only one output. Alright, we've already said that. In order to be over here, each input has only one output, but then also each output has only one input. So if that's the case, this function is called one-to-one, and this will be important when we talk about inverses later on in the semester. Alright, so I hope you kind of see the breakdown here. Functions are a subset of relations, and in order to be one-to-one, I first have to be a function and then satisfy this second criterion that each output has only one input. Alright, so we're going to look at a couple examples here with various representations and decide, are these functions, and if so, is it one-to-one? Alright, so my first one, my input is the student and the output is a student's phone number. Okay, so let's think about that. Could a given student have more than one output, more than one phone number? Well, yeah, maybe the student has a home landline, a mobile phone, a dorm number, a work number. So it is possible for a student to have multiple outputs here, more than one. All right, so this is not a function. All right, well, if I'm not a function, there's no way I can be one-to-one. All right, so I have to first be a function before I can be one-to-one. So I'm not a function and it's not one-to-one. Okay, now next we're going to input the student and get out the student's dorm. So would it be possible for a student to live in more than one dorm? Well, no, you can only live in one. So this is a function. So now we need to check that second criteria. Is each dorm associated with only one student? Well, no, hopefully there's more than one student per building, right? So no, this is not one-to-one. Okay, here we're going to input a student and output that student's student ID number. So each student has only one student ID, so this is a function. All right, now each ID number is associated to only one student. So yes, this is one-to-one. All right, now let's look at a numerical representation. Here, my input of 1 has an output of 3. My input of 2 has an output of 3. My input of 3 has an output of 3. Input of 4 has an output of 3. Now, each of these inputs has only one output. Only one. Only one. All right, so this is a function. Now, it is not one-to-one. Do you see that 3 here, this output of 3, is associated with 4 different inputs? So it is a function, but it's not one-to-one. So this would be similar to the dorm example we just looked at. All right, next, let's see here. 1 is associated to 4. 4 is only associated to 1. Okay, so that one has only 1. This one has only 1. 2. Yep, that's only 1. 3 is associated only to -2, and -2 only to 3. And lastly, 4 to 5, and 5 only goes to 4. So yes, this is a function, and it is one-to-one. All right, now here's a tricky one. Look here at 3. If I tell you my input is 3, do you see 3 is associated with 2, but it's also associated with 5? So this one is not a function. Okay, and if we're not a function, we cannot be one-to-one. So that is a numeric representation. All right, let's see here now. These are tough. We got to think a little abstractly when we have an algebraic representation. If I plug in a number here, let's call it 1. 2 times 1 would give me 2, minus 5 gives me -3. I only get one output. So yes, this is a function. Okay, now the tough one is figuring out, is this one-to-one? Is it invertible? If I know the output, so let's say my output is 15. I'm just making up a number here. Is there only one x that could give me 15? Well, do you remember solving equations? I add 5 to both sides and I get 20, divide both sides by 2 and I get 10. So I only get one result. So yes, this is one-to-one. All right, if this is not obvious to you, which it could be tough, you might want to graph it and then use that vertical line test and horizontal line test that you might have learned in algebra. So this function is going to look like a straight line here. All right. Okay, so if this is my function, do you see each input value, each x is associated with only one output, f of x? Or the way that you might have learned it is if I drop a vertical line, it hits it in only one spot. That means each x has only one y. Well, similarly, you can drop a horizontal line to see if it's 1 to 1. And again, I hit it in only one spot, so yes, each y has only one x. Alright, so this is definitely the most difficult using an algebraic representation. So let's look at this one, x squared. If I plug in a value, do I get only one output? So let me plug in 2. If I plug in 2, I square it and I get 4. Yeah, I just get 1. Now the tough part is going the other way. So it's definitely a function. Now, let's say I know my answer is, or my output is 9. Is there only one value for x that I squared and give 9? Well, no. Maybe it's 3, or maybe it's -3. Do you see how both of those, if I square them, give me 9? So this is not 1 to 1. All right, let's go back to our graphical representation. X squared looks something like this. Okay, so if we were to graph this, our vertical line test, draw a vertical line, it hits it just once, we pass, so yes, we're a function. All right. However, if we do a horizontal line, let's say this was 9 here, we have one value here at -3 and another one here at 3, so this is not 1 to 1. So vertical line test, 1, if it hits it once, it's a function. Horizontal, if it hits it once, it is 1 to 1. All right, now this one is tough because there's no x here. Every single input, the output is 4. So this is very similar to one we just saw. This one right here, the output value for everything in this one was 3. Well, the one we're looking at right now, the output for everything is 4. So it is a function. If I plug in 1, well, there's nowhere to plug it in, but the only one result, 4. If I plug in 2, only one result, 4. So it is a function. All right, however, this is not 1 to 1. All right, it is not 1 to 1 because the output of 4 is mapped to every single value. So again, if I could draw this somewhere up here at 4, we have a horizontal line. Okay, it certainly passes the vertical line test, but it fails horribly this horizontal line test. Because see, every single value here is 4. So I passed the vertical, but failed the horizontal. All right, next, a mapping. So I think the algebraic representation is the toughest. So if we have this little mapping here, 4 goes to only 1, 5 goes to only 1, -3.5 goes to only 1. And similarly, if I go the other way, each one has only 1. So this is a function, and it is 1 to 1. Alright, now this one's difficult because let's look at 5. Do you see 5 has 2 different outputs associated with it, 4 and 5, so this is not a function. Alright, and then if I'm not a function, I cannot be 1 to 1. Alright, now With graphical representations, we can just use our vertical line test and horizontal line test. So here, let's try first vertical, right? Everywhere, if I draw a vertical line, that hits just once. So this is a function. Alright, now let's try a horizontal line test. That hits just once, and hopefully you guys can draw your horizontal lines more horizontal than I am doing here. But again, I'm only getting one input for a given output, so yes, this is 1-to-1. Alright, next, this one, if I draw a vertical line, oops, I got one here and one down here, so this is not a function. Alright, and then if I'm not a function, I cannot be 1-to-1. Alright, now here's a graphical representation. Vertical lines pass only once, so this is a function. Now, look here, if a horizontal line here, oops, I did not draw that very horizontally, but hopefully you guys can do a better job than I'm doing. Do you see I have multiple inputs for a given output? So this one is not 1-to-1. Alright, 3 more than the square root of a number. Alright, so if I take a number, I'm going to find its square root and add 3 to it. This would be a verbal representation. So let's just pick a number and try one. Let's take, I'm going to pick a number that I can take the square root of. So let's say I take 4. Okay, I take the square root of 4, and remember we said there are 2 roots here. I can have 2 and -2. Alright, then I add 3 to both of these, and I get 5 up here and 1 down here. So for a given input of 4, I ended up with 2 different outputs. Okay, now if this said principal square root, then we would be okay. But because it does not say principal square root, we got 2 different outputs for a given input, so this is not a function. Alright, and then if I'm not a function, I cannot be 1-to-1. Alright, the smallest whole number greater than a number. Alright, so let's say I pick 2. Alright, the smallest whole number that is greater than 2, which would be 3. Okay, let's say I pick 2.5. The smallest whole number greater than 2.5 is 3. Okay, let's say I pick -2. Now this one's tricky. Now think about your whole numbers. Remember, whole numbers were the natural numbers, the counting numbers, and 0. So what is the smallest whole number that's greater than -2? I think that would be 0, because that is the smallest possible whole number. What about -2.5? 0. What about -17? That would be 0. Alright, so for in each of these cases, for the input, I had one output, so this is a function. Now, it is not 1-to-1, because do you see that both of these, if I say my output is 3, there were more than one number that can give me 3. If my output is 0, there are tons of values that could give me 0. So this is not 1-to-1. Alright, and then here we have another numeric representation. So our inputs are in the left, outputs on the right. So 1 goes to 4, 3 goes to 6, 2 goes to 7. Now let's see here. This is tricky. Do you see 3 is mapped to both 6 over here, but then it's mapped to 7 over here? So I'm going to say this is not a function. Therein, it is not one-to-one. Alright. Okay, next we have here 1 goes to 4, 3 goes to 6, 2 goes to 7. Alright, so I think each input has one output. Yes, so I think this is in fact a function. Right, 1 has only one output, 3 has only one output, 2, yep. Now if we look the other way to see if it's one-to-one, 4 goes to only 1, 6 goes to only 3, 7, oh, 7's troublesome. Do you see 7 is mapped to both 4 and 2? So this one is not one-to-one. Okay, this brings us to our last objective for today, which is constructing a completely defined model. Now, again, we'll do this over and over again, both in this course. If you move on to take business calculus, you'll do it there too. So for today, what I think is most important is that you realize if I ask you for a model, there are 4 parts. Okay, we're going to do this over and over again in the next 3 chapters, so you will get better at this. But for today, think model, 4 parts. Alright, the first part is an equation. Okay, so this is a mix of an algebraic and a verbal representation. So I need an equation, but if I want to use your equation, I need a little more information. I need to know what your input is and what your output is. So the next thing I need you to do is describe the output with units. Alright, and remember, think output is what you traditionally called Y. Okay, now I also need you to describe the input with units. Okay, and the order of those is not important. The order of any of these isn't important. But in order to use your equation, I need to know what does your input variable stand for in the context and what does your output variable stand for in the context. Now the last piece I need is the domain. Alright, and this tells me where I can use the equation. Alright, so if you think back to the example of the falling object, right? Let's see if we can find that one. Nope. Right here. Alright, do you see our domain here was from 0 seconds to 8.081 seconds? Well, it would not make sense to use this equation that we have here to find the height of an object 20 seconds after you drop it. Okay, it's not going to be underground. So I need an equation, which well, let's look at this one, which we have. Okay, I need to know what the output is, the height. I need to know what the input is, the time. And the last thing I need is a domain. I need to know where it makes sense to use this equation. Alright, so these are the 4 parts of a model. So let's look at a couple examples here. So now here I give you models. These are written out as a narrative. Some students prefer to bullet the full 4 parts. That's fine. Alright, so let's see if we can find the 4 parts. So let me just read it first and then we'll go back and find the 4 parts. So the function f of x here gives the yield of kumquats in thousands of pounds, where X is the amount of rain that season measured in inches for 3 to 15. Alright, so the first piece is right here. That's the easiest one. We have an equation. Perfect. Alright, now we need to describe the output. What is this F? Well, this function gives the output of this is the yield of kumquats, and our units are 1,000 pounds. So this is my output. Alright, then next I need an input description. What does X stand for? Well, X here is the amount of rain, and my units there are inches. That is my input. Alright, and then lastly I need some sort of domain, and here my domain is from 3 to 15. So maybe if it rains less than 3 inches, we didn't get enough rain to produce a crop, and more than 15, we washed it out. Alright, so those are the 4 parts of a model. Let's look here at this next one. From 1973 to 1980, the number of traffic accidents in Spartanburg can be modeled by this equation here, where X is the number of years after 1900. Alright, so let's see here. The equation is the easy one. I found the equation. Now, what is my output? What is G? Well, the output here is the number of traffic accidents. Alright, now we need an input. What was the input here? What is X? X is years since 1900. Alright, so let's say if I wanted the number of traffic accidents in 1975, I'd take 75, because that's how many years after 1900, plug it in here, and get out the number of accidents. Alright, lastly, I need a domain. Where can I use this? Well, it tells me right here, this is only going to work for years between 1973 and 1980. So that is my domain. Alright, so hopefully from those examples we can identify the 4 parts of a model. Now, let's see if we could construct a model. Now, this is a little tougher. So we want to construct a model for the number of bowling pins in this arrangement based on the number of rows. Alright, so what I might do to help me, I might start over here and make a little chart here, see if that helps us. Alright, so if I have 1 row, well, I'll start here, 0 rows. If I have no rows of pins, I have no pins. If I have 1 row, I have 1 pin. If I have 2 rows, I have 3 pins. If I have 3 rows, I have 1, 2, 3, 4, 5, 6. I have 6 pins. And then if I have 4 rows, I have 10 pins. Alright, now this is a tough one, which is why we're doing it together. I wouldn't give you one this tough on the homework. But if we can do this, we can tackle all the ones in the homework. The first piece of my model I need is an equation. Now, how might I come up with an equation here? Now, this, I'm not adding the same amount, right? Do you see here? I add 2. Here, I add 1. Here, I add 3. And here, I add 4. Now, we'll talk about this in great deal in the next chapter, but this isn't going to be a simple linear equation. So I'm going to give you a clue here. So let's start with 0. If I take 0 times 1, I get 0, which is what I wanted. Okay. If I take 1 times 2, I get 2. But it didn't work there, right? I only wanted 1. If I take 2 times 3, I get 6. Oh, that's not what I wanted. I wanted 3. If I take 3 times 4, I get 12. Do you see I'm always getting double what I'm shooting for? If I take 4 times 5, I get 20, but I only want 10. Alright, so I'm going to give you the equation, and let's see if I can convince you that it works. Let's say my equation here, I'm going to say P of R is going to be R times R plus 1, but then I need to cut it in half, 2. Let's see if that works. Alright, so let's try it here. 0 times 1 more than 0 is 1, gives me 1. No, that is completely wrong. 0 times 1 gives me 0. I take 0 and I cut it in half and I also get 0. Yep, that worked. Alright, so it worked there. Let's try it here. 1 times 2 gives me 2. Divide it by 2 and I get 1. Yep, that worked. 2 times 3 gives me 6. Divide it by 2 and that gives me 3. Yes. Alright. 3 times 4 gives me 12. Divided by 2 and get 6. Yep. 4 times 5 gives me 20. Cut it in half and I get 10. Yes. Alright, so it looks like my equation works. Do not stress if that equation did not jump out at you. That is tough. What is important are the 4 parts of the model today. Alright, so I came up with the equation here. Now, we need an output. So the output here, P, is the number of pins. This equation here gives the number of pins Alright, so we've got an equation. I described the output. I have units there, pins. Now we need an input description where R is, well, my input here was the number of rows. R is the number of rows. Alright, now we need a domain. Now this domain, it might even be easy just to list the domain. Do you see that there are only 5 values in my domain? 0, 1, 2, 3, and 4. So one way might be to list them. You could say X is 1, 2, oh, I forgot 0, 3, 4, or 0. Okay. Or this is an alternative. I'll put it in a separate color. You might say 0 less than or equal to R less than or equal to 4, but I need one more little piece of information. Do you see you couldn't have half a row here? So I might say and a whole number. Either way, as I did here or in red here. So we have our 4 pieces of the model, right? Number 1, an equation. Number 2, the output. Number 3, the input. And number 4, the domain. And once again, don't stress if that equation didn't jump at you. That's a tough one. Alright, now this one, much more manageable. Let's see here. A rectangular garden has a perimeter of 500 feet. We want a model for its area. So I'm going to draw a little picture here. I think this will help me. So we want the area. So A of W, I might call this. The area inside here. When my input is W, the width. Alright, now, what makes this tougher this is W, and this is W. Now to find area, you take length times width. But how in the world am I going to figure out what this piece is? Well, that's where I have to use this piece of information. Alright, the perimeter is 500 feet. So if I were to go all the way around, start here, and take this side, this side, this side, and this side. All four sides are 500. Well, I already said I'm going to call this one W. And I'm going to call this one W. So I've used up, I know what those are. So to make this a little simpler, let's just go halfway. Because those are the same, right? If I just go halfway, and I have 500 feet, what do you see if I just go halfway? I've used 250. Alright, so if this, all this green stuff is 250, and I've used W here, this is going to be 250 minus W. Alright, so to come up with my equation here, I'm going to call it A of W. We're going to take W times 250 minus W. Alright, so that is the equation. Length times width, or width times 250 minus that width. Now I need an output description with units, an input description with units, and a domain. So my output here is A of W, or the area. So this gives the area. Now I need units for area. Let's see, my width is in feet. So if I took foot here, so many feet here, times so many feet here, we get square feet. You might write this like this, square feet. Alright, so there are my units, where W is the width. Now the width is just in feet. Now the tough part is the domain. Let's see here. It can't be negative, for sure, right? You can't have a negative width. Now, here's the tough part. At some point, you're going to run out of fencing. Do you see if my width was 300 here? Well, then I use 300 over here. That's more than 500. So it can't be 300. Let's see if I did 200 and 200. Yeah, then I have 100 left over here, so that'd be 50 and 50. So at what point would one of these become negative? Let's look at this piece right here. This is going to help us. If we look at this piece. If this W, do you see if I use more than 250 right here, then I use 250 here, and then I have nothing left there? So my upper bound here, if I look at this piece, I don't want my length to be negative, so the width can't be more than 250. So my upper bound here is 250. And again, don't stress if that was tough for you. What is important for today is that we have 4 parts to a model: an equation, an output description with units, an input description with units, and a domain.